Okay, welcome all in this hybrid meeting in the room and on Zoom on our weekly TCS seminar at Jagiellonian. In this hybrid form, it never feels like a seminar, but it is. Well, today we have our speaker is our intern this semester, Clément Rambaud. He came to us, he's finishing ENS in Paris. And he is here with us on his research intern. What we do here is mostly structural graph theory, but the results Clément is going to talk about today are from his previous internship with Benjamin in Brussels, right?
Exactly.
So please, Clément, the floor is yours.
Thank you. Thank you, Chad. Okay, so I will talk today about the neighborhood complexity of planar graphs. So this is a joint work with Gwenaël Jovet from the Université Libre de Bruxelles. So before talking about neighborhood complexity, just a few words about classes of bounded expansion. So this is a notion introduced by Necettril and Bossona de Mendes 15 years ago, and it's a very general notion of sparse graphs. So there are really a lot of concrete examples of classes of bounded expansion, and here are just a few of them. So for example, the class of planar graphs is a class of bounded expansion. The class of graphs with maximum degree at post some constant is another example. Graphs excluding a fixed minor, graphs excluding a fixed topological minor. So all these classes have bounded expansion. Okay. So this is a notion which is quite useful in algorithmics, and a lot of problems that are hard in general becomes easy when we are restricted to a class of bounded expansion. So I just mentioned this Milsa theorem, which says that first order model checking is polynomial time tractable in a class of bounded expansion in linear time. So concretely, if we want to know if there exists a dominating set of size k, we can answer it in time a function of k times n in such a fixed class. Whereas in general, it's not possible because it's a problem which is W too hard, and so from the complexity theory, this is not possible for every graph, but in a class of bounded expansion, we have much better algorithms. Okay, so what is the definition of classes of bounded expansion? So there are a lot of equivalent definitions of classes of bounded expansion. And today I will focus on a characterization using neighborhood complexity. So what is neighborhood complexity? So we have a graph G in a class C of graphs, and A, a set of vertices, R is an integer that I will call the radius. And we look at the following quantity, which is the number of possible intersections between A, this set of vertices, and balls of radius R. So when I say ball of radius R centered on the vertex V, this is just a set of vertices at distance at most R in the graph. Okay, so for example, here in this figure, we have, if we look at so the balls of radius 1, so for R equal 1, we have 6 singletons for the balls centered on the vertex on A, which are the red vertices. And there are 7 other possible intersections with A, between A and the ball of radius 1. Okay, so in general, this quantity is always at most 2 to the A because it's a family of subsets of A, so of course it's at most 2 to the A. But actually, if C is a class which is sparse, which is a class of sparse graphs, this is much smaller. So we have this theorem, which says that in a class of bounded expansion, there exists a function f, such that for every G in my class, for every A subset of vertices, for every radius R, this quantity, so the number of intersections between A and all of radius R, is at most f of R times A. So instead of having something exponential in A, we have something linear in A where the radius is when the radius is fixed. Okay, and actually it's a characterization of classes of bounded expansion. So under the condition that C is closed and not taking subgraph, this property characterizes classes of bounded expansion. Okay. Okay, so now if I have such a class of bounded expansion, I define the neighborhood complexity of this class to be the smallest function f that satisfies this inequality for every G in the class, for every A subset of vertices, and for every R in the. Okay. So now we'll look at the neighborhood complexity of planar graphs. So the goal will be to determine as precisely as possible the neighborhood complexity of planar graphs. And so concretely, the question is, what is the smallest function f, such that for any planar graph G, for any set A of vertices, for any radius R, the number of intersections between A and the ball of radius R is at most f over times A. And our goal will be to determine this function. So the result I just mentioned before shows that f of R exists, and actually it gives also an effective upper bound. So f of R is at most 2 to some polynomial. Okay, so this is an explicit upper bound, but it's not very precise. And it was recently conjectured that actually f can be taken polynomial in R. Be a polynomial in R. Okay. So this is the conjecture, and we solved this conjecture. So we proved that in a planar graph, the number of intersections between A and balls of radius R is always a big O of R4 times A. So the neighborhood complexity of planar graph is big O of R4. Okay. Okay, so here, so I talked about neighborhood complexity, but actually it will
be... I have a question already.
Sure.
Because I remember that in Marek's, because this is from Marek's thesis, right?
Yes.
I remember that he had a number of results, also for planar graphs, bounding it.
Yes.
But I guess it wasn't linear RNA. What was it?
Yes, I think it was R7 times A cubed.
R to the 7.
I think.
Okay.
It was not linear in A.
So you had polynomial in A times polynomial in R, right?
Yes.
But, okay.
Exactly.
And it was open if you can get it linear in A.
Yes, exactly.
I see.
Okay, so actually it will be more convenient to work on what I will define to this profile complexity. So first I define the profile of a vertex on the set A of vertices. So the profile of V on A is a function that maps a vertex of A to its distance to V, if this is at most R and to plus infinity otherwise. So this is an object that contains more information than just the intersection between A and the ball of radius R, because not only we remember this intersection, but also we remember all the distances between V and the vertices in this intersection. Okay, so this is an object which contains more information, and there are at most first easy remark, there are at most R plus 2 to the A R profiles on A, just because it's an A tuple of values between 0 and R or plus infinity. So we have this trivial upper bound. And now what I will define to be the profile complexity of a class C is the smallest function f, such that for any graph in the class, for every set A of vertices, for every R, the number of R profiles on A is at most f of R times A. So maybe it's not defined, but we'll see that in a class of bounded expansion, it is indeed defined. And this is clearly an upper bound of the neighborhood complexity, just because it's an object that contains more information. So there are more profiles than just the number of intersections between A and balls of radius. Okay, so profile complexity is an upper bound for the neighborhood complexity, but actually they are almost equivalent because of this lemma. So if C is a class with a reasonable condition on it, but really you will see it's not very, it's not much to ask. So the profile complexity is at most R plus 1 times the neighborhood complexity. So what does that mean? Well, we have a graph G in the class, a set A of vertices, and we want to bound the number of profiles we have on A. Okay. And to do that, we consider a new graph where we put a path of length R on every vertex of A. Okay, so this is a new graph, and if C is nice enough, this graph is also in the class. This is what I mean by C reasoning. So now if we call A prime with the union of the vertex sets of all these paths, I have the following properties. Number of R profiles on A is at most the number of intersections between balls of radius R and A prime, which is this larger A. So why is that? Just because if I look at the vertex V, and if I look at the intersection between the ball of radius R centered on V with A prime, is the union of all these paths, from this intersection, I can recover the profile of V on A. And this is just because if I take a vertex on A and I want to know the distance between V and this vertex, I just look at the furthest vertex I can reach on the path corresponding to this vertex of A. And this distance is the distance between V and the vertex of A. Okay. So this is just a simple observation. But now, so the consequence is that the number of arc profiles on A is that most the number of intersections in this new graph between A prime and all the points R. But if this new graph is in the class, well, this is at most the neighborhood complexity that we call F of R times the size of A prime, but A prime is just R plus 1 times A. So we get this upper bound. So from a bound on the neighborhood complexity, we obtain a bound on the profile complexity. And up to a factor of R, these two notions are equivalent. Okay, so it will be more convenient to work on profile complexity, and we will see later why. So we'll see now. So for trees, let's start with trees, which is a simple example. So we will bound the neighborhood complexity of the class of every trees. Okay, so a tree is given. Let's root it arbitrarily to the vertex and say it's a root. And consider a set of vertices which is given. So here it's the right vertices. Okay. So to bound the number of profiles on A, we'll consider this set A prime. So A prime is defined to be the set of vertices which are an ancestor of a vertex in A at distance at most R. So concretely, for every vertex of A, we add to A prime, well, this vertex of A, and its R first ancestors. Okay, so this is a set of size at most R plus 1 times A. And why we do that? Just because we have this nice claim. It says that for every vertex of the tree, in A or outside A, for every vertex of the tree, there exists a vertex W in A prime that I will call a guarding vertex. So this means that W intersects every VA path of length at most R. And why this is true? Just because okay, consider V such a vertex, and we take W to be the first vertex in A prime on the path from W to the root, if it exists, and otherwise we take it arbitrarily. Okay, and now if you consider some VA path, the path between the V and the vertex of A, it has a minimum for the relation parents are smaller than children. Okay. And this minimum is an ancestor of both V and the vertex in A. So it belongs to A prime because it's a vertex of A of a vertex in A. So it's an ancestor of a vertex in A at distance at most R. So this minimum of the path belongs to A prime. And now we choose W to be the first vertex in A prime on the path from V to the root. So in particular, W intersects every path between V and A. And so it intersects this path. Okay, that's all. And why we are happy with that? Because now if I want to know the profile of my vertex V, I just need to know first my vertex W, and second, the distance between V and W. Because now the profile of V on A is just the profile of W on A, translated by adding plus the distance between V and W to every coordinate of this A tuple, which is the profile. Okay, just translate the profile. We just move forward. Okay, and so now the number of R profiles on A is at most the number of possibilities for A prime. So this is R plus 1 times A at most, and the number of possible distances between V and W. But actually, if this distance is larger than R, we can say it's just plus infinity and forget it. So there are at most R plus 2 possibilities. So in total, this gives big O of R squared times A. So here you see, when I say that we don't need to remember the distances larger than R, another way to say it is just to say that I only need to remember the profile of V on the singleton W. And with this point of view, we can really generalize this reasoning. And this is what we will do now. Okay. So to explain the general strategy to obtain a good upper bound on the neighborhood complexity, I need to introduce the notion of guarding set. So what I will call a guarding set for a vertex V is a set U of vertices that intersect every VA path of length at most R. So we have our set A of vertices, which is fixed. So the radius R is fixed too. And U is a guarding set for V if every path between V and A must intersect U or is larger than R, or length larger than R. Okay. So why this definition is useful? Because now if I want to know the profile of V on A, it's enough to know U and the profile of V on U. So it's not very hard to prove. It's just because the distance between a vertex of V, the vertex V and the vertex of A is the minimum of all vertex of U of the distance between V and this vertex plus the distance between this vertex of U and the vertex considering R. This is just an elementary observation on the distance. Okay. And so now if I know the profile of V on U, I can recover the profile of V on the whole set A. Okay, so this will be a tool. And now we can describe the general strategy. So the strategy will be to build a family of sets of vertices such that every vertex has a guarding set in this family. This family is not too large, meaning it's some polynomial in R times A. Okay, and for every member of this family, the number of R profiles on this set is at most polynomial in R. And if we have these three conditions, then the number of R profiles on A is at most some polynomial in R times A, just because the profile of a vertex V is completely determined by its guarding set and the profile of V on this guarding set.
The number of R profiles on U is at most independent of the size of.
We will build a family of sets which are small, so that this is small. So typically, in the first example we'll see just after, it will be for graphs of bounded tree widths, and U will be the member of this family will be just bags basically, and so they will have small size. Okay. And we can prove that the number of profiles on such a set is polynomial in R. Okay. And yes, maybe it will be clearer with the example of graphs of bounded tree widths. Okay, so to just the definition of graphs of bounded tree widths. So what I will call a tree decomposition of graph G is a tree T and a family of subtree of this tree indexed by the vertices of G. And the conditions I need is that, okay, T is a tree, every TV for V vertex of G is a connected subtree of T, and every edge of G is realized as a non-empty intersection between TU and TV. Okay, so we just want to realize G as an intersection graph of subtrees, and maybe some edges are missing. Okay, so now with this definition of bag, the bag of a node X in the tree is a set of vertices whose corresponding subtree contains X. Okay, and the width is just the maximum size of a bag minus 1. Okay, so here is just an example of a bag. So the bag of this vertex is just this set of vertices in the graph. Okay. We need one more tool to deal with neighborhood complexity of graphs of bounded tree widths, which is recurring numbers. So the setting is the following: we have a graph G, and suppose we have a total ordering of the vertices, a linear ordering of the vertices of G. Now we say that W, a vertex W, is weakly reachable from V at distance at most R if there is a path from V to W of length at most R, such that the minimum of this path, according to the total ordering, is W. Okay, so we can use only vertices which are on the right of W, never the vertices on the left. Okay, and now the goal is to minimize the size of this set, the number of vertices weakly reachable from V, and the recurring number is the minimum of all the linear ordering of V of G, of the maximum number of vertices weakly reachable from V, as the maximum taken of vertices V. Okay, so this is a notion very, very interesting for itself. It also characterizes classes of bounded expansion. There are a lot of applications, but here we'll only use some very simple facts about this. Okay, so an example in a tree, If we take a total ordering such that A is smaller than B, if A is an ancestor of B, I suppose that my tree is rooted. So there is a notion of ancestor and children, etc. So A is smaller than B if A is an ancestor of B. So of course, this is not linear ordering. So, but we can take any linear extension and it will work. And now with this ordering, vertices which are reachable from a vertex V are exactly its R first ancestors and V itself. Okay, so why is that? Just because, okay, so these vertices are clearly reachable, just take the path. It's okay. And why, for example, this vertex is not quickly reachable? Just because, well, when we look at the path from B to this vertex, the minimum is an internal vertex. It's not the extremity of the path. Okay. Okay, so from this remark on trees, we can lift it to graph some bounded tree width using a tree decomposition. So there is a very natural ordering we can take if the graph has a tree decomposition, which is A smaller than B if the root of TA is an ancestor of the root of TB. Okay, so we look at the vertices which are the highest in the tree TA and in the tree TB, and we compare them in the tree. Okay, so again, this is only a partial ordering, but we can take any linear extension, and that will do. And now, with such an ordering, there is this theorem, which says that the number of vertices quickly reachable from a given vertex is always at most R plus T choose T. So it's at most R to the T big O of R. Okay. So why is it useful for us? Because now we can really extend the reasoning we had on trees to graphs on bounded tree. So suppose you have a graph with of bounded tree width with a tree decomposition of widths at most T. Okay, and a set A of vertices which is given. Now consider A prime to be the set of vertices which are quickly reachable from A. So there are not too many of them. There are at most O of RT times A because of this theorem. Okay, and now we have the following claim. For every vertex V of the graph, there exists W in A prime such that the root bag of the TW intersects every VA path of length at most R. So again, this claim is almost the same as in trees. Just, okay, to find this W, you consider, so your vertex V, you look at the root bag of TV, root bag containing V, and look in the tree at the path from this bag to the root, and you take W to be the first vertex so that the root bag of W is in this path. Okay, so this is really exactly the same thing as for trees, but lift it. We lift it using the tree decomposition. Okay, so now we have this property. Yes.
So the definition of W is that you start from the root bag of V.
Yes.
You go in the tree up towards the root. And where do you stop?
When you find a bag, which is the root bag of W for W in A prime.
Oh, for W in A prime.
Yes. And it works because now if I take a path between V and A, I take the minimum of this path. And this minimum is weakly reachable from A. I mean, yes, the vertex in G is weakly reachable from A. And so if I choose W such that W gets every path between V and vertices weakly reachable from A, which is exactly what I'm doing by this process. I will intersect every VA path of length at most to know if it makes sense. It's okay.
So I'm struggling with some, because path from B to A. So why can't you just take a bag containing the root of V? Then you also
yes, true. But here we want, okay, the goal is to build a family of guarding sets, which is as small as possible. And so here we choose W in a small set. Okay, the set we build is chosen among the family, which is quite small.
So
and this is why we were happy. Because now my family of Garding sets is just this family of rulebacks, so from TW for W in A prime. So this is a family of sets of packs, and this family has size at most the size of A prime, which is at most R to T times A.
Okay. There is some guarding the condition that maybe he doesn't have any path at all, right? And then you don't have a bag.
Yes, but in this case, you can choose it arbitrarily, or
that's actually true.
Yes, okay. And the profile will be constant to plus infinity. Okay, and now the consequence of that is that the profile of V on A is completely determined by its guarding bag and the profile on its guarding bag. Okay, so the number of guarding bags is at most R plus T choose T times A, and the number of profiles in the bag. And the bag has size T plus 1 at most. This is always at most R plus 2 to the T plus 1. So in total, the number of profiles we can have in A is always at most a big O of R to the 2T plus 1 times A. Actually, this can be improved. This plus 1 can be removed because we don't really need all the bag. We can take just the adhesion with its corresponding child. But okay, it's a detail, but we can remove this plus 1.
So the R plus 2 comes from the number of different values on the coordinate of an R profile, right?
Exactly. Exactly. We just need to remember all the distances on the bag, which has size T plus 1, and distances larger than R, we can forget them.
So 0 to R and then infinity.
Exactly.
R plus 2. Yeah.
Exactly. Okay. So now we will move to planar graphs, and we will use the product structure theorem. So this is a theorem which decomposes graphs, planar graphs, as a product of two simple graphs. So the notion of product we will use is the notion of strong products. I will not define it formally, but just it's the notion of product of graphs, such that the product of two paths is a grid like that. Okay, you have diagonal in the cells, in every cell of the grid. Okay. And so this theorem says that for any planar graph G, there exists H and P, such that H is a graph of true width at most 8, or some constant. P is a path, and G is a subgraph of H times P. So G is a subgraph of something like this, where every row is a copy of P, and every column is a copy of H, which is bounded true width. So every vertex of H corresponds to a copy of a path, and every vertex of the path corresponds to a copy of H. Okay. So why it's useful for us to bound the neighborhood complexity and more generally to profile complexity. So the first step is to reduce to the case where P has size big of R. And actually, this is not very hard, just because you can cover a path by intervals of size roughly for R that overlap like this. And now, if you look at the ball of radius R, it will always fall into one of this interval. And so it's enough to focus on one interval of size for R, and then at the end to sum the number of all the profiles on all the smaller instances. Okay, so I'm a bit quick, but this is easy. It's not hard. So now suppose that P has size U of R. Okay. So the idea is to project A, the set of vertices which is given, on H. So we can do that. Okay. And now using that, we can compute the guarding sets in H. And this we can do because H has 3 widths at most 8. So by doing this, we'll get a family of guarding sets of size at most R plus 8 choose 8 times A, which is big O of R to the 8 times A. And now, what is a guarding set in this family? Well, it's a set of at most 8 plus 1, so at most 9 vertices of H. But this corresponds in my original graph to 9 copies of a path of length R, big O of R. So every guarding set that I built like this is a set of size big O of R in my original graph. Okay. And now the claim is the following. For every vertex in the graph, there exists a guarding set in this family. So when I say guarding set, it means that it intersects every VA path of length at most R. And this set has size big O of R. Okay. So now we can try to bound the number of profiles on A. So we see that most the number of guarded sets times the number of profiles on a guarded set, which is a set of size big of R. And of course, the first factor here is not a problem. It's at most R8 times A. But for the second one, we have a problem because we want something polynomial in R. But of course, for graphs of boundary tree width, we are just saying, okay, number of profiles on a set of size t plus 1 is at most R plus 2 to the t plus 1. Here we cannot do that because we get R to the R. It's not polynomial. And so to solve this problem, we'll need some VC dimension argument. So the VC dimension is a notion introduced by Papnik and Sherpo. Okay, I forgot the name. But okay, this is a notion of complexity of an hypergraph. So it's the VC dimension of an hypergraph with branch set V and E set of hyperedges. It's the maximum size of the subset X of vertices, so that when we look at the intersection between X and the hyperedges, we can do all the subsets of X. Okay, so all the subsets of X are realized by intersection with an hyperedge. And now this dimension is the maximum size of such a set. And yes, so that's for the definition of VC dimension. And a very fundamental property of VC dimension is the Soerschler lemma, which says that the number of edges is always at most the number of vertices to the VC dimension. Okay. So now we will apply this on the hypergraph of balls in a planar graph. So consider G a planar graph, and consider the hypergraph where the hyperedges are just all the balls of all the radius possible. Okay, and then there is this theorem which says that this hypergraph has VC dimension at most 4. It's not very hard to prove. Very nice observation. And now the consequence is that when I take a set B of vertices, the number of intersections with B and between B and the ball of radius R, this quantity is always at most B to the 4th, just because of Soerschler lemma and this theorem of VC dimension. Okay. And now we will use this to bound the number of profiles on a small set of size big O of R, because in a planar graph now the number of profiles on the set B is always big O of RB to the 4th. And why is that? It's always the same reduction if we glue a path of length R on every vertex of B. Now, if I look at the intersection between this larger set and B and the ball of radius R, I can deduce the profile in the original graph. Okay, this is the same argument. So the number of profiles on the set of vertices B is always big O of R4 times B to the 4th. And this is the inequality we wanted, because now the number of R profiles of A is that the number of guarding sets times the number of profiles on the set of size big O of R. So the first factor is just big O of R8 times A, and the second one is big O of R to the 8. And so we get finally this polynomial on the number of profiles of A. Okay, so the number of R profiles on A is at most big O of R to the 16th times A. And so the neighborhood complexity of planar graphs is polynomial. Can we do better? So the answer is something better. Yes, we can do. We can really do much better because we managed to improve this 16. We replace it by 4. Okay, so the number of R profiles on A is big O of R4 times A. Okay, and now I will explain you how to obtain this much more precise bound. Okay, so before doing that, just the method I presented just before using product structure can be really improved using some more precise version of the product structure theorem and things like that. But to obtain such a precise bound, we need to go deeper into the structure of a planar graph. Okay, so the main idea is to use a much more precise VC dimension argument. So this result was pointed out by Jacob Holm, Eric Van Jan van Leven and Marcin Pilipczuk. So we are really grateful to them for that, because we really missed this result. So this result says that if B is a vertex set of a face in a planar graph, so if B is a vertex set of a face, then the number of R profiles on B is big O of R times B cubed. Okay, so before we had just R force times B force, and here we have R times B cubed. Okay, so of course we have a strong hypothesis on B, but now the goal will be to build a family of guarding sets, so that every guarding set, on every guarding set we can apply this lemma. So basically we want guarding sets that are faces in some sense. Okay. And to do that, well, first step, we do some easy cleaning. So you can assume that every vertex is at distance at most R from a vertex of A. Otherwise, its profile is plus infinity, and okay, it's one profile, so this profile is counted, and now we focus on the other ones. And so you can assume that every vertex is at distance at most R from A. And you can assume that G is connected, otherwise you just process connected component independently and you sum the number of profiles at the end. Okay, so the second step is to reduce to the case where A is the outer face. And here you can use really as a black box a lemma by Sokołowski, which says that, okay, if we allow to multiply by big O of R the size of A, we can suppose that, basically. So this is not very formal, but I can still give the idea of the proof. So because every vertex is at distance at most R from A, and because the graph is connected, you can find a tree that contains every vertex of A and which has size big O of R times A. This is, there is no difficulty here. And the idea is to cut along this tree a new face. So we'll open this tree and create a new face. Let's say it's the outer face, okay? And now the observation is that if I know the profile of a vertex B on this outer face in this new graph, I can recover the profile of V on A in the original graph. And again, it's easy to see. Okay, so this is a very, very nice lemma. And now we have a planar graph where every vertex is at distance at most R from the outer face, and we want to bound the number of profiles on this outer face. Okay. And here, now we will really actually build the family of guarding sets. And the idea is the following: we'll build a graph H such that H is almost a subgraph of G. So there are some edges that are missing, but okay, this is a technical detail. A prime is, so what I call A prime is the vertex set of the outer face. So the vertex set of the outer face A prime is a subset of H. Okay. The number of faces of H is at most big O of A prime over R, and every face of H has size big O of R. Okay, so this is approximately what we want to prove. And why this is useful for us? Because now all the faces of H will give the family of guarding sets. Because when I take a vertex of G, I can look at which face of H was interior contained it. Okay, and now the boundary of this space is a guarding set for my vertex. Okay, and the idea to prove this is really relies on some ideas of the product structure theorem, of the proof of the product structure theorem. And basically what we are doing, we start with H being just the outer face. And as long as there is a face which is too large, of size really bigger than R, we split it into 3 smaller faces. Okay, so that's the idea of the proof. Okay, so now the conclusion of all that. The number of R profiles on A, this is at most the number of guarding sets. So here guarding sets are just boundaries of faces of H, so they are at most A prime over R of them, times the number of R profiles on the face of size big O of R. Okay, but here we can use the more precise lemma I just mentioned with slide before, which says that this is big O of R4. Okay, because this lemma was saying that if B is a vertex set of face, number of profiles on B is big O of R times PQ. So here, yes, say big O of R, we obtain R to the fourth. Okay, so A prime is the outer face here, and in the original graph, this and A prime is a set of is a vertex set of is a set of vertices of size at most R times A times the constant. Okay, this is because of the lemma of the previous slide. Okay, so finally we get this upper bound. The number of profiles of A is big O of R to the fourth times A. Okay, so this was for this much more precise upper bound on neighborhood complexity of planar graphs, and even profile complexity, actually. And of course, natural question is, can we go further than just planar graphs? First, what happens if we look at graphs embedded on a surface? Okay, so have this result. If G is embeddable on a surface of genus G, then the number of R profiles in A is big O of R4 times R plus A. Okay, so basically it's the same neighborhood complexity. Okay, of course the constant in the big O depends on G. Okay, so the proof here is not very hard. Basically, we cut every time we see a torus, we cut it using a small cycle, and it decreases the genus. So this is quite standard argument for graphs of bounded genus. Okay, and we can also generalize it to KT minor free graphs. So for every T, there exists a constant CT which depends on near T, such that every KT minor free graph G, for every set A of vertices, for every R, the number of R profiles on A is big O of R to the CT times A. Okay, so the profile complexity, and so the neighborhood complexity of KT minor free graphs is at most polynomial in R. And here the proof uses Robert-San-Seymour graph minor structure theorem. So the constant CT is not very explicit. Okay. Okay, so KT minor free graphs are nice, but can we go beyond? And the answer is, well, not really. Of course, we can build we can give some construction of a class which excludes no minor and still have polynomial neighborhood complexity. But if we look at the natural class, actually, it has super polynomial neighborhood complexity. So, for example, if we look at one planar graph, so one planar graphs are graphs that can be drawn on the plane where every edge is in at most one crossing. Okay, and more generally, K-planar graphs are graphs that can be drawn on the plane with at most K crossing per edge. Okay, so this class is still nice because we have a product structure theorem for this class. So the tree width is slightly different, but we really have a product structure theorem of the same form, of the same shape. So this is a class we can hope for a polynomial bound, but actually no, this is not true. And the construction is the following. So we'll build a family of one planar graphs together with a set A of vertices, such that the number of profiles on A is at least 2 to the square root R, basically.
These edges, they cost more than once.
Yes. Okay, but now I will explain the construction. First, we will build a square root R planar graph, and then we will subdivide the AG square root R times to get one planar graph. Okay, so what is the construction? We start with square root R vertices, A1, A2, up to A square root R. This is our set A. And on every of the vertices, we root a complete binary tree of depth, which is square root R. And we can draw them like this. Okay. And now for every leaf,
what is the depth again?
Square root R. Yeah. And then we will subdivide it square root R times. So this will give distance R.
So what vertices in A are stable set?
Yes. Yes.
Where are the vertices of A?
It's the roots of all the this complete binary trees. Okay. So each of this binary tree has 2 to the square root R leaves. Okay. And so we can index them by subsets of 1, 2, 3 square root R. Okay. And now for every of these subsets, we add a new vertex and we connect it. So for example, the vertex corresponding to 1, 2, we add a new vertex for this set and we connect it to the leaf numbered 1, 2 in the first tree and the leaf number 1, 2 in the second leaf. Okay, we just connect it to the tree corresponding to the number in the set. Okay, and why we do that? Just because now if we look at the intersection between the ball centered on this vertex and
wait.
yes,
I didn't get the construction.
sorry.
No, it's so you have leaves. The number of leaves is roughly 2 to the square root r, right?
Yes, for every tree.
For every tree, and then you enumerate the leaves with the subsets.
Yes.
Of what set? Of
1, 2, 3 up to square root r.
Okay. And then you introduce a new element, a new leaf. How again? For each one?
We introduce a new vertex for every such set.
Okay, and what is the rule?
And now we connect it. Okay, for the set 1, 2, we connect it to the leaf which is just above him in the first tree and in the second tree, and not in the third one. We just connect it to the trees according to the set. Okay.
But because the trees are also numbered by these.
Yes, there are square root r trees.
Square root r trees. Okay, so the numbers indicate to which trees.
Yes, exactly.
And to which leaves are you attaching again?
I'm attached to the leaf numbered with the same set. So really like in this drawing, okay, we can group the leaves corresponding to the okay, like this.
I see. Wow. Okay.
And we just connect them.
Nice. Okay.
Is it clear?
Yes, yes. Nice construction actually. I've never seen something.
Okay, so now if you look at the ball of radius r centered on this new vertex, say the vertex corresponding to 1, 2, if we intersect this ball with a1 to a square root r, we obtain exactly a1, a2. Okay, and this is true in general. We obtain exactly the set of vertices in A corresponding to the set labeling this vertex. So we have 2 to the square root r distinct intersection between A and balls of radius r. And of course, this is at distance square root r, but the graph is not one planar. So now we subdivide every edge, which is square root r times. And now the graph is one planar. And now if we look at balls of radius r, not square root r, we have at least 2 to the square root r distinct intersections with A. So here is an example of a one planar graph where the number of r profiles and even the number of intersections between A and balls of radius r is at least 2 to the square root r. Okay. And so this shows that the neighborhood complexity of one planar graphs is at least 2 to the square root r divided by square root r. And so this is super polynomial. Okay. How much time do I have? Okay, perfect. Okay, so now on this slide, I will talk about an extension of neighborhood complexity to a more general first order formula. So the observation is that the intersection between A and a ball of radius r, it's exactly the set of vertices in A that satisfies the formula. The distance between V and A is at most r. And now we can replace this formula distances between V and A is at most r by some other first order formula. So maybe just one remark why this is a first order formula, because we can encode distance between V and A at most r as a formula. There exists a path, so the idea is that it's a path, but there exists vertices x1 up to xr, such that x1 is A, xr is V, and xi plus 1 is an edge for every I. Okay, so we can encode this formula as this property as a formula of length big O R. Okay, and so more generally, we can look at this quantity for any first order formula. And there is this very nice result which says that in a class of bounded expansion, this quantity is at most some function of the formula times A. Okay, and actually it's an if and only if the class is closed under taking the graph. So this is really something much stronger than just characterization of classes of bounded expansion using well, no, it's not really stronger, but it's different. But it's a big generalization of the result about neighborhood complexity that characterizes the classes of bounded expansion. Okay, and of course, now we can ask what is the smallest function f such that this is satisfied. No. Does it make sense?
Is a subset of A.
Yes. We look at the subset of A such that this formula is satisfied, such that phi of VA is satisfied. So, for example, if phi of VA is the formula that encodes distance between V and A that is R, this subset of A is just the intersection between A and the borrow price R center of B. No. It's okay. And okay, so we proved that in the specific, very particular case where phi encodes the formula distance between V and A that must R, we proved that f here can be taken polynomial for the class of planar graphs, of course. And of course, we can ask, is it true for general formulas? And the answer is no. And the reason is because one planar graphs are interpretable from planar graphs. So this means that we can simulate one planar graphs from a planar graph just using a first order formula, fixed first order formula of constant size. And so using the previous construction of on one planar graphs, this shows that we cannot hope for a polynomial bound for f here. So,
what's their function? Is it like a tower or is it like just?
No, it's just square root r, something like 2 to the square root r.
Okay.
Just because we.
It's pretty tight actually. That's only go on.
Ah, you mean the upper bound? Ah, I don't know. Ah, sorry, I was thinking about the lower bound. So the lower bound is 2 to the square root of the pi, basically. And the upper bound, I have no idea. Sorry. We should check, but this is probably larger.
It's just probably this guy mount.
Yes. Yes, because we want to use the same idea that the guarding set. If I know enough information on this guarding set between V and this guarding set, I can deduce what happens behind it. But I don't know much on first order formulas. That's not the logic. Okay, so this was just one slide for this remark about extension of neighborhood complexity. And
so it'd be interesting to actually ask for what kind of formulas you have polynomial bound, yes?
mm-hmm.
Maybe you can describe it somehow. Maybe there's a interpretation.
Yes, maybe. I don't know. Okay, so to finish, I want to explain you the construction we have for the lower bound on the profile complexity of graphs of Krivitz at most t. And this will give us for Krivitz to a lower bound for planar graphs. So what we'll prove is that for every t and r, there exists a graph of Krivitz at most t, and the set A of vertices in this graph, which has the number of r profiles on A is some big omega of r to the t plus 1 times A. Okay. So this will show that the profile complexity of the class of graphs Krivitz at most t is a big omega of r to the t plus 1. So the proof starts as follows. So first for Krivitz 1, so we will build a tree. We'll take this graph. So this is, we have two vertices, A1, A0. We link them with a path of length R/2. And on every vertex of this path, we add a new path of length R/2. Okay. So in total, this gives R squared over 4 vertices. And now what I claim is that all the vertices, they have distinct profiles on A0, A1. And why is that? Just it's a change in the coordinate system. Okay, because the distance to A0 is the sum of the x coordinates plus the y coordinates, and the distance to A1 is the sum of the x coordinates plus minus now the y coordinates, maybe plus R2. Okay, and so we have this linear system, and this linear system is injective. And so all vertices have distinct profiles. So we have R-square distinct profiles on A0, A1. And now for true width 2, we add a new vertex A2, and we link it to all the leaves in the previous step with a path of length, say, R3. Okay. So we add some small path here. This is just for a technical reason. We don't want to create shortcuts like this. And now on every path in the for every vertex of that were in the previous construction, we add a path of length R3, something like that. Okay, so this has now size R3, and every small path here size R3. And now we claim that again, the profile of every vertex in this main three-dimensional grid is completely determined by its profile on A0, A1, A2. Okay, so all distinct vertices have distinct profiles on A0, A1, A2. And again, this is just because when we write the coordinates and the profile according to the X, Y, Z coordinates, this gives a system of three equations. This system is injective, and so they all have distinct profiles. And now we can again repeat it. If we want true width 3, now we add a new vertex A3. We link it to all the leaves here. Okay, and now we glue a new path of length R/4 now on every vertex here. And again, this system can be solved clinically. And okay, and why the graph built like this have small true widths? Just because, okay, for true width 2 here, it's just because it's a 3 plus 1 vertex, so it has true width of 2, and each time we add one more vertex in and so yes, this has more true width for a very strong reason. Okay, so this was for the construction of for this lower bound, and now to finish, just some application of all these results. And it's an application of, about a metric dimension. So the metric dimension of a graph G, it's a smaller size of a set A of vertices, such that the profiles at distance plus infinity on A distinguish the vertices. So this means that we have a set A, which is called the resolving set, I think, such that the profile of a vertex on A completely uniquely determines this vertex. Okay. And now we don't care, there is no R, we look at distance plus infinity. So now if G is a n-vertex graph with metric dimension K and diameter D, well, n is at most D to the K plus K, because we have K profiles we have K vertices, sorry, for vertices in A, and for vertices outside A, we have at most the number of possible profiles on A, which is a K tuple of integers between 1 and D. Okay, so we have at most D to K possibilities. We can refine this upper bound, but it's not very important for us. And recently it was the question of having better bounds for specific class of graphs has been investigated by this group of authors. And in particular, they proved that if G is kt minus 3, then n is at most a big O of D to the t minus 1 times K to the t minus 1. Okay, so this is much smaller than D to the K. And if the tree width of G is at most T, then n is at most a big O of D to 3T plus 3 times K. And actually, our results on the profile complexity, the corollary is following inequality. So first, in a class of bounded expansion, n is at most some function of the diameter times K. And as far as I know, we are the first to notice this, which is a bit strange, but okay. If G is kt minus 3, then n is at most some polynomial in D times K. And if the proof that G is at most T, then N is at most big O of T to the 2T times K. Okay, which is better than 3T plus. Okay, and now to conclude,
So they don't
yes.
the constant, the KT minor figures in their result is concrete, which means that they don't go through the Robertson Simon, right?
Yes. This is just the VC dimension actually. Because okay, a long time ago I was saying that the number of profiles on a set B is at most R to the 4 times P to the 4,
Yes.
using the fact that the hypergraph of balls in the planar graph is at most 4. Actually, the hypergraph, the VC dimension of the hypergraph of balls in KT minor graphs is at most T minus 1.
Oh, okay.
And so we have the same one. But they don't prove it exactly like this by gluing paths like us. They are doing something slightly different, but
the dimension of balls is there, so it was before.
No, yes, this is known. So for planar graph, it was Chepoy, Access, and okay, I forgot the name, but it was written. And otherwise, it's Nicolas Bousquet and Stéphane Thomasé for KT minor graphs. It's not very hard. You take a system of balls that gives all the possible pairs. Actually, you don't even need the whole VC dimension. You don't even need to create all the subset of say B by intercelling by paths. You just need to be able to build all the pairs. Okay, and you have all the pairs. And if you take the balls of minimal size, I think if you minimize the size of the balls, the radius, you obtain a minor, basically. That's all.
Yes.
Okay, so this was for the metric dimension. And now, just to conclude, a few open questions. So, of course, our goal was to determine as precisely as possible the neighborhood complexity or the profile complexity of planar graphs. And we have this upper bound of R to the 4th, and this lower bound of R cubed, and for the profile complexity. Of course, it would be nice to fill this gap. Same question for fluids at most T. So we know that it's between R to the T plus 1 or R to T. And finally, is it possible to find a polynomial bound for the neighborhood complexity of KT minor graphs without using Robertson-Simons theorem, and so to get much more explicit bounds? I think it might be possible, but we failed. We tried, but we failed. Okay, and that's all I had to say. Thank you very much.
Thank you so much.